What we did with the heated electrospray design was base it off our successful APCI probe technology. The heater on the APCI probe is well established, it's robust, so we wrapped a heat exchanger around this heater. Now the idea is to swirl the auxiliary stream of nitrogen gas around the heat exchanger. The swirling causes an increase in path length, which causes the gas to pick up heat. It comes out of a slot, which is the auxiliary gas slot, interacts with the primary spray and causes a reduction in droplet size in the source housing. So that raises the sampling efficiency into the vacuum system of the heated ion transfer tube and the tube lens assembly. Sampling a dry droplet or dry ion is always beneficial. The tube lens works better. You focus the ion into the skimmer and you get an enhancement in signal and a reduction in droplet size. So this technology gives you an enhancement in signal to noise, which will directly impact the sensitivity of your assay.
The quantum in our laboratory, primarily the HSI source configuration, we use for low-level quantitative work. We use that for both blood and urine samples we get from the racetrack. A lot of times we're trying to distinguish a therapeutic drug at a threshold level, so we need parts per trillion capability. We've used it for drugs like clenbuterol, and being able to establish a regulatory threshold for clenbuterol in the low parts per trillion, where we didn't have adequate detection a few years ago. The new source design and new capability of the quantum has allowed us to see those drugs in the low parts per trillion, 10 to 5 parts per trillion. We establish a regulatory threshold for clenbuterol at 25 parts per trillion in plasma samples and racehorses. In that case, we used actual horses at the racetrack, collected samples from nearly 30 of them, and used that to establish our regulatory threshold. What we found with the newer technology is that we were getting better desolvation and therefore better ion source generation. We were able to get more ions into the detector and therefore allowed us to reduce our background noise by increasing the total number of ions that we put into the detector, which gave us significant increases in sensitivity. The improvement in the ion generation process allows us to see those low parts per trillion that we've so much desired to see over the last 10 years. Very visible now with minimal background issues, primarily because of the changes in the source design, allowing that ion to transition without causing any destruction of our analyte on the way.